All right, so yeah, so YouTube works this time, thank goodness. Fingers crossed that it keeps working. All right, so on Monday, what did we talk about? Well, we started talking about recursion, right? So recursion is a problem-solving strategy where you solve a problem by solving smaller versions of the same problem, right? And we went through some examples like factorial. We talked about how to do recursion with linked lists, but with list sum and appending to the end of a list. And we also looked at how to use recursive helper functions, right? Because sometimes you can't use the function that you're given recursively. You have to create a helper function that can do the right thing and recurse through the list and so on. So now we're going to finish up the last few parts of this lecture. Right, so let's talk about Fibonacci. So Fibonacci is a classic example of recursion, and you probably know what the Fibonacci sequence is. So it's the sequence where every number is the sum of the previous two numbers, right? And you have two numbers at the start, which are 0 and 1. So the sequence would go like 0, then 1, then 1, then 2, then 3, then 5, and so on. Right, if you look up the definition of the Fibonacci sequence on Google or Wikipedia, you'll basically see this, right? The 0th Fibonacci number is 0, the first Fibonacci number is 1, and then for all other numbers in the sequence, f of n equals f of n minus 1 plus f of n minus 2. So this really makes it easy for us to implement Fibonacci recursively, because the implementation would basically just be this, like these three formulas, right? So if we were to implement Fibonacci, it would kind of look like this, right? If n equals 0, return 0. If n equals 1, return 1. Else return fib n minus 1 plus n minus 2. Right? Now, this is a really nice and elegant solution, right? But let's see what happens when we try to run it. Right, I've got my Fibonacci program here. Right, so it contains the exact same code that I showed on the slide. And the program just takes in a command line argument, which is the n that you want to find the Fibonacci number of. And then we can run it like this. So fib1 is 1, and fib2 is 1, fib3 is 2, and so on. So you can see that it works. Okay. Now let's see what happens when we try to time the program. So to time the program, we put time before the program. So let's try seeing how long it takes to get the 10th Fibonacci number. So that's pretty fast. It takes less than 0.01 seconds. Right. Let's try 20. So still really fast. Now let's try 30. Let's see what happens. So, all right. So it still seems to be doing well, right? What happens if we try and get the 40th Fibonacci number? So now it's starting to take a long time, right? So it's gone from 0.01 seconds around to more than a second, right? So, and then let's try finding the 42nd Fibonacci number. Right, so now it's taking 3 seconds. So every time we try to find the next Fibonacci number, it takes even longer and even longer. And yeah, from fib 42 to fib 43, it takes more than 50% extra time, right? So what is the problem with this implementation? It looks so elegant, right? So shouldn't it run really quickly as well? Well, the problem is what happens with the recursive calls that it does, right? So if we try and draw up a tree of all the recursive calls that this function does, let's look at an example for fib5, right? So fib5, we can see that fib5 calls fib4 and fib3, right? Then fib4 calls fib3 and fib2, fib3 calls fib2 and fib1, fib2 calls fib1 and fib0, and so on, right? So the problem with this implementation is if you look at the tree, you'll see that there are a lot of repetitions, right, in the function calls that are made, right? Fib3, for example, is called twice, right? And fib2 is called 3 times. And you can imagine that if we try to find the next Fibonacci numbers like fib6, fib7, and we drew a tree of those function calls, then we would get an even bigger tree with more repetitions in it, right? So the problem is the function's repeating a lot of computation, right? But it shouldn't need to, because once you've computed fib3 once, you shouldn't need to compute it again, right? So yeah, and what ends up happening is that the number of recursive calls grows exponentially, right, as n increases. And the time taken by the function will increase exponentially as well. So this is just an example of a case where recursion is not so great, right? So can be horribly inefficient. And for this example, Fibonacci, it's best to just use the iterative implementation, where you just use a loop, right? So yeah. Okay, so last thing I wanted to talk about. Sorry? Iterative. So here's what the iterative implementation looks like. Okay, so yeah, basically it keeps track of the previous 2 Fibonacci numbers, and then it calculates the next one, and then it saves that one, and then calculates the next one, and it saves that one, calculates the next one, and so on. So not too much to it. All right, so last thing I wanted to talk about was recursion versus iteration, right? So how do they compare? Like, is a recursive solution going to be faster, or is the iterative solution going to be faster? You know, which one's going to use more memory? So generally, if there is a simple iterative solution for a problem, a recursive solution will generally be slower. Right? And the reason for that is when I showed you the factorial example earlier, we see that when we run the factorial function, it needs to create multiple stack frames, right, for each recursive call. Every recursive call needs to have a stack frame created for it. So creating a stack frame does cost some time, right? So that's why the recursive solution is generally slower. Meanwhile, if you use an iterative solution, you only have one function, right? And that function just runs, and it doesn't take as much time to run because it just has a variable, right, that just keeps getting updated. Okay, and how about in terms of memory? Well, same diagram. If we have a look, right, we run the factorial function recursively, right? It needs to create stack frames on top of stack frames on top of stack frames. So the factorial function uses a lot of memory, right? The higher the factorial you want to find, the more memory it's going to use, right? Meanwhile, if you use a loop, right, all you need to do is just loop from 1 up to n and then multiply repeatedly, right? So it doesn't use nearly as much memory as the recursive solution. Yeah, question. Good question. So the question was, when is recursion better than iteration? Yeah, so So there are some benefits of recursion. One is that so there are some data structures that are really easily manipulated with recursion, but are more difficult to solve with iteration. And we'll see examples of that, I think, in week 3, where we start talking about trees. The trees are kind of branching structure. It's kind of hard to loop through a branching structure. So there we tend to use recursion. Yeah. Sorry? Yeah, deleting a binary tree, yeah, that is easier done with recursion, yeah. We'll look at that in week 3 as well, probably. Yeah. All right. So any other questions about recursion? Okay. Well, let's move on then and talk about the topic of today, which is analysis of algorithms. All right, so analysis of algorithms is a really important topic. That's because it's one of the major themes of the course, right? We want you to be able to analyze your algorithm in order to determine how feasible it is, right? When the input size increases, right? So your algorithm might be really fast when you run it with 100 data items, right? But when you run it with more data items, like 1,000, 100,000, a million, how well is it going to scale, right? And all of that depends on how efficient your algorithm is, right? If you've made the right choice of data structure or algorithm, then it'll scale pretty well. If you've made the wrong choice, then it might not run as quickly, right? Okay. So, right, what's the motivation? So, well, program runtime is critical for many applications. So finance, robotics. So there are a lot of applications where you want your program to be fast, right? And sometimes, why we might want to analyze our algorithms is that we want to compare 2 programs, right, to decide which one to use, right? So you've written a program, your friend's written a program, whose program is better? So you can analyze your algorithm to determine that. So also, we want to be able to determine if our algorithm is going to be fast enough, right, for our purposes. Right? So you don't necessarily need to run your program on 10 million data items. If you know how to analyze your algorithm without even running it, which we can do and which we'll talk about, then you don't even need to implement your algorithm, right? So yes, let's have a look. So yeah, so we want our programs to be fast, right? We want them to be efficient. So what determines how fast the program runs? So the operating system might affect how fast the program runs, or compilers might affect how fast the program runs, right? When you compile your program with different compilers, they might generate different machine instructions, which might affect how fast the program runs. Compilers might also have an optimizer option, right, which will cause them to try and apply optimizations to your program. Hardware also determines how fast your program runs, right? So how fast is your CPU? How fast is your GPU? Do you have a cache, right? So things like this all determine your program speed, and also the load on the machine, right? So if there are lots of users on the machine at the same time, which is what the CSE servers would be like, close to an assignment due date, then the program might run a little slower, right? Because there are lots of users on the machine at the same time. But by far the most important determiner is the data structures and algorithms that you use, right? So we'll focus on analyzing algorithms in this lecture. All right, so think about an algorithm, right? So we will give the algorithms an input and it produces some outputs, right? So how long is that algorithm going to take? Well, the running time of the algorithm tends to be a function of input size. So what that means is that how long the program algorithm takes will depend on the input size. And why is that? Well, because the algorithm's probably going to have some loop in it, right, that looks at all of the data items or some of the data items, and the more data items there are, the more time the loop will take, right, to look through the items. Right, so what we see is that typically the larger your input gets, the longer the program's going to take. Right? And if you have a small input, right, lots of algorithms are going to run really quickly on it, right, because computers are pretty fast in general. Right? So regardless of the algorithm, if you have a small input, programs will run really fast. But if you have a larger input, then your program is going to run slower, but how much slower is going to run? Right? So in this graph, I've got run times of 3 different algorithms. So a good algorithm isn't going to get much slower as you increase the input size. Right? A reasonable algorithm will increase a little bit more, but it'll still be feasible for large inputs. Meanwhile, a bad algorithm might run well in small inputs and medium inputs, but as the input size gets larger, it might become infeasible. Right? Okay, so when we're analyzing an algorithm, what do we actually want to analyze? So there are different cases that we might want to analyze. Right? So the first one could be the best case performance. Right? So you want to see what is the fastest, what is the least amount of time that my program could possibly take, right, to run. Right? So you could analyze this, but it's usually not very useful, right? Because the best case usually depends on you feeding it a specific type of input. Right? So for example, let's suppose you're trying to run a sorting algorithm, and the sorting algorithm checks whether the input is sorted, right, before doing anything. Then, then it would run really fast if you give it a sorted input, right? But how often are you actually going to pass it a sorted input? It depends. So the next kind of case is average case performance, right? So you're trying to analyze how well the algorithm is going to perform on different kinds of data. Right? But this is often difficult because you need to have a good idea of what inputs your program is going to take in. Right? You need to know how the program is going to be used, and ideally for each type of input, how frequently is it going to be passed into the program. Right? So measuring average case performance is quite difficult. So what we tend to do is just look at the worst case performance. So what is the worst that could possibly happen? What is the longest amount of time that the program could possibly take? Right? And this is the most important type of case to analyze, right? Because it determines how long your program could run. And if you have a time constraint that says, well, your program shouldn't run longer than this amount of time, and in the worst case it could, then you might not want to use that algorithm. Right? All right, so so how do we analyze the efficiency of a program? Right, so there are 2 main ways. One is to do it empirically, and what this means is you implement the algorithm in a program, then you run it, and you see how long it takes. Right? And there's the second way, which is theoretically, and what you do there is you look at the algorithm, you could look at the code or the plan of the algorithm if you haven't implemented it yet, and you basically count how many operations it performs, right, as a function of the input size. So we'll look at empirical analysis first. Right, so how does empirical analysis work? Well, we write a program that implements the algorithm. So then we run the program with inputs of different sizes, different types. So an example of different types of inputs might be, have sorted inputs, you have random inputs, and you have reverse sorted input. Right? Those are some typical inputs you would pass into a sorting algorithm to see how fast it would run. Then you would measure the runtime, then you plot the results, right? And then you see what kind of trends the algorithm has. Okay, so how do we measure the program's running time? Well, we can use the time command. So the time command, you run it by just typing time before the actual command that you would run usually. So for example, time./program. And the time command will produce 3 different times. So the first time is the real time. So this is the total elapsed time between when the program starts and when the program finishes. Right, so it's as if we started stopwatch when the program begins, and then when the program ends, we stop the stopwatch. Right? And the real time, it needs to be interpreted carefully because it can be affected by how much load there is on the machine. Right? If there are lots of users on the machine at the same time, then each program is going to run slightly slower, right? Because the CPU has to divide its time between all of the users and their programs. There's also user time. So user time is the CPU time the CPU time spent executing the program's code. Right? And finally, there is system time. So system time is the CPU time that's spent by the operating system on behalf of the program. Right? So sometimes your program might have to talk to the operating system. For example, when it opens a file, it needs to ask the operating system to open the file for you, and that counts towards the system time. Right? Another example is when you have to allocate lots of memory, right? Your program has to ask the operating system to allocate that memory for you. Okay, and if you look at the timing results here, we can see that the program doesn't spend a lot of time in system operations, and the user time is 0.38 seconds, and the real time is 0.44 seconds. Right, so we see that there is some, so there is some time difference there, right? 0.06 seconds, which means that probably the CPU is spending those 0.6 seconds, executing some other program, right? Not this program that's being timed, right? Okay, so when we measure program runtime, we want to figure out what kind of trends the runtime has, right? So if we just measure, the program runtime with one input or one input size, that's not going to tell us much, right? So, look at this graph. Suppose if we just measure how long the program takes on one input size, right? It just gives us 1 point on this graph, right? But it doesn't really tell us the trends, right? Because if you run it on another input size, how much is the time going to grow? So you want to run your program on multiple input sizes, and also, so the thing with running your program, timing your program, is that you're not purely analyzing the algorithm, right? Because you're implementing the program in a specific programming language, then you're running it on a specific machine, so you're introducing a lot of other factors, right, by timing your program. So what you should do when you do empirical analysis is to make sure to run your program, time your program on multiple input sizes. Right? Because what we're really interested in is the trend as the input size increases. Okay, so what I want to do now is run some empirical analysis on linear search. Right, so what is linear search? Well, linear search takes in an array, its size, and a key to search for, and it loops through the array until it finds the key. Right? Once it finds the key, it'll return the index of that key. Otherwise, it'll return -1. Right, so I've got the program here. Right, so linear search, let's try and run the program normally first, just to show how it works. So we enter the array size, we enter the values of the array. So I'm just going to say 1, 2, 3, 4, 5. Right, and then it asks me to search for a key. So let's search for something that's in the array, right, 4. So it'll say that we found 4 at index 3. Okay, now let's try running the program and giving it an item that's not in the array. So let's search for 6. And it says did not find element 6. All right, so let's have a look at the program code quickly. So the linear search function is the same as what I showed in the slide. I return the index of the given key if it exists, or -1 otherwise. And what does it do? It scans in the array size, scans in the array values. So similar to this week's labs, actually. Then it scans in a key to search for. Then it calls linear search. Right, so yeah, so now I want to time this program, but when I time the program, I don't want to enter all the input by myself, right? Because that would stuff up the timing results, because I'd have to, it would count the time that I spend typing, right, as part of the user time. So what I have instead is I have another program that doesn't require me to enter anything. Right, so what this program does is it just takes in the size of the array that I want to test as a command line argument. Right, then it creates an array of that size. Right, so notice that I'm just mallocing here. So all the elements in the array are going to be uninitialized. Then I search for this value, -99. And it's most likely that -99 isn't going to be in the array, even though I haven't initialized anything. Right, so I call linear search, and then I don't print anything either, because I don't want to get any output. Yeah, so let's try and time how long this program takes. So it's called linear search 2. So I'll put time and say linear search 2. And I need to specify the array size. Right, so let's try 100. Right. If we only have an array of size 100, the program's going to finish pretty much instantly, right? Because the programs just, computers are really fast, and going through an array of 100 items is trivial, right, for a computer. So let's bump up the input size a little bit. So let's try 1,000. Well, it's still very fast with 1,000 elements, so let's try 10,000. Well, it's still very fast, so let's try 100,000. Right, so it's still very fast, computers are very fast, and let's try a million. Right, so it's still very fast. Let's try 10 million. Right, so now we can see that it's starting to take a little bit more time. Right, if we look at the user time, it's taking 0.029 seconds, whereas before it was taking about 0.004 seconds. Right, so now let's increase it to 100 million. So we can see that it's taking quite a bit more time now, right? 0.274 seconds as opposed to 0.029, and it's pretty consistent, right? When we run it, it always hovers around 0.27, 0.274. All right, and let's see what happens when we have 1 billion elements. Right, so now it's starting to take a few seconds. Right, so 2.7 seconds. So yeah, so this is the trend, right? And I've ran all of this before the lecture, and I've got some of the results here. Let's see if they're similar. So looks like at the moment it's running a bit slower than when I did it before. So that's okay though. So what is the trend here, right? So the trend seems to be a linear trend, right? Because if we look at if we look at when we increase the time from 10 million to 100 million, for example, we're multiplying the input size by 10, right? The runtime also approximately increases tenfold, right? Not exactly, but it's close. And when we increase the input size from 100 million to a billion, which is 10 times the input size, the runtime also increases tenfold, right? So if I ran this if I ran the program on 10 billion items, who can guess, how long it's going to take approximately? Yeah, 24 seconds, right? Because the trend seems to be a linear trend. So if we increase the input size by 10 times, the runtime should also increase by 10 times, right? And 10 times this is about 24 seconds. Right, so our conclusion from running this empirical analysis is that the worst case runtime of linear search grows linearly as the input size increases. Right? And I didn't explain I didn't explain the fact that we were testing the worst case. Right? But if we look at the algorithm, right, clearly the worst case would be when the element that we're searching for is not in the array, right? Because the function would then have to loop through all the elements of the array before returning -1, right? So if the element was in the array, then it would stop somewhere in the middle and then return I. But if it's not, then it has to go all the way to the end. So that would be the worst case. Right, what would be the best case of linear search? Yeah. So the best case, so the best case would be where the first element in the array is the element that we're searching for, right? And in that case, if we times the function for the best case, it would remain consistent, right? No matter how large the array was, because the function only needs to look at the first element. Okay. So that was a demo of empirical analysis. And empirical analysis has its limitations, right? So first of all, it requires us to implement the algorithm, right? And implementing the algorithm might be difficult, right? It might not be as simple as linear search. There are a lot of complicated algorithms out there. We might not want to spend our time implementing the algorithm in order to time it. Another limitation is that your choice of input data will affect the results that you get, right? And depending on what input data you give your program, you might come to different conclusions about, how efficient the program is, right? So choosing good inputs is extremely important when you're doing empirical analysis. All right, so next is quite similar to the previous point. So, so time results, Yeah, timing results are greatly affected by the runtime environment. So, you're running your program on a machine, right? So how long your program takes will depend on the load on the machine, right? Will be affected by the load on the machine. Yes, and also, if you're doing empirical analysis to compare two programs, then you need to make sure that you implement the programs in a comparable way, right? So you should make sure that you implement both programs in the same language, for example, because different languages will have different program speeds. Right? So you wouldn't want to implement one algorithm in C and one in Java or Python, for example. Right? And you'd want to make sure that they're compiled with the same compiler on the same machine. And then when you time the program, you have to make sure that you use the same inputs. Make sure you run the programs on the same hardware, right? So if you run them both on your laptop, then that would be ideal. Same operating system and same load, right? So yeah, so that's empirical analysis. Now, does anyone have any questions about that? All right, so we will press on then. Okay, so the next thing we want to talk about is the other analysis method, which is theoretical analysis. Right, so theoretical analysis, in theoretical analysis, we're counting the number of operations performed by the program, right, by the algorithm. So because we're just analyzing the algorithm itself, we don't necessarily need to implement the algorithm, right? Instead of analyzing the code, we could analyze the pseudocode of the algorithm, and we'll talk about pseudocode next. And, well, we could use the code if it's implemented already, but usually we analyze the algorithm before implementing it, right? Because if it's not efficient, then there's no point implementing it. Okay. Okay, so theoretical analysis, what we'll get is we'll end up characterizing the running time of the function or algorithm as a function of the input size, right? So what we'll get is we'll get how long the program takes to run as a function of the input size. So the input size will be n, and your runtime might be something like 2n squared, right? Okay, with theoretical analysis, because we're not running the program, timing it on different inputs, our analysis will aim to take into account all possible inputs, right? So when we're analyzing the worst case, for example, we'll look at the algorithm and see, what if there are if statements in the algorithm, or what path what path would my algorithm take if it were to take the longest possible time, right? So we'll take into account all possible inputs when we're analyzing our algorithm, and in the end, theoretical analysis will let us evaluate how efficient the algorithm is, regardless of the environment. Right, so the nice thing about theoretical analysis is that it's free of any environmental variables, such as the operating system, the machine, the load, and so on. All right, so let's talk about pseudocode. So the reason we talk about pseudocode is that when you're analyzing an algorithm, right, you might not have implemented the algorithm yet. Right? You might just have an outline of the algorithm. You might have something written up, right, that resembles code but isn't really code, right? And that would be pseudocode. Right? So pseudocode is a plain language description of the steps in an algorithm, but it's structured. Right? So it has things that you would see in an ordinary programming language. Right? So it have if statements and loops and so on. And it would be nicely structured, so it would be indented so you can see where all the control structures are and so on. Right? And in pseudocode, we tend to omit language-specific details. So what I mean by that is we wouldn't have variable declarations like ints. We wouldn't have semicolons or open braces, closed braces like that. Yeah. So here's an example of a pseudocode for linear search. So, so how is the pseudocode formatted? Well, we have the function name at the top, and we have the inputs, and then we describe the inputs and outputs, and then we have some fairly readable language here. So for this obviously obviously indicates a for loop. Right, so for I from 0 up to n-1, then so do is just part of the pseudocode, and then we have an if statement. So if a at index I is equal to key, then return I, and otherwise at the end return -1. Yeah. Yeah, so there's no standard for pseudocode, because it's not an actual programming language. So you don't need to write your pseudocode this way. We won't prescribe a specific convention of pseudocode. So you could write things differently. For example, if you don't like the end for and end if, you don't necessarily need it. As long as you can clearly indicate the structure of your code, it will be fine. Okay, so when we analyze our algorithm, theoretically, we rely on the fact that there are some basic operations, right? So every program can be, broken up into a set of basic operations, and then our job is to simply count how many times each operation runs. Right? So every algorithm uses a core set of basic operations. So examples of these are assignments. So this would be assigning to a variable, indexing into an array, right? Calling, returning from a function. So evaluating an expression. So there are lots of different expressions, but examples would be like addition, subtraction. There are Boolean expressions like and or. There are comparative expressions like less than, greater than, and equal to. So all of those. And then increment and decrement are some other examples. So we call these operations primitive operations. Okay, so because they're very low-level operations that every program, no matter what language it's implemented in, would end up being broken down into these operations. Okay, and one assumption that we make is that primitive operations take a constant amount of time. Right? And we can also assume that they take the same constant amount of time, even though that's not necessarily true like in a real machine. It won't affect the result that we get. So, yes. Okay, so counting primitive operations. So we're going to look at the linear search algorithm again, and this time we're going to do theoretical analysis on it. All right, so what we want to do is determine the worst case of linear search, right? So we'll try and determine what is the maximum possible number of primitive operations that are executed by linear search as a function of the input size, right? So the input size is how many elements are in the array, right? And then, which is n, and then we find how many operations the algorithm performs in terms of n. Right, so let's try and count how many primitive operations there are here in the worst case. So first of all, we have a for loop, right? And with the for loop, like it starts from 0 and it goes up to n minus 1. So, how does the for loop really work? So how do we count the primitive operations there? Well, we sort of have to imagine how it'd be implemented in an actual programming language. Right, so if we look here, I've given one suggestion as to how this might be implemented in C. Right, so we got a for loop where we create an integer I and initialize it to 0. Then our condition is I less than n, and then we have an increment I plus plus. Whoops. So how do we count the primitive operations here? Well, first of all, there is an assignment statement here. Right, so that counts as one primitive operation. Then we've got a condition. Right, so how many times does the condition get checked in total? Well, it gets checked once at the beginning. Right, so when I is set to 0, it'll check immediately whether I is less than n, and then the loop is gonna iterate n times, right? And at the end of each iteration, it'll check the condition again. So this condition gets checked n plus 1 times, right? And then the increment, so how many times does the increment occur? Or it occurs n times, right? So initially, the value of I is 0, then it increments to 1, then it increments to 2, and it will stop once it increments up to n, right? Because then the condition will be false. So the increment occurs n times. All right. Now we have the if statement. And remember, we're considering the worst case here, right? So this would be the case where the element that we're searching for is not in the array, and we have to go all the way up to the end. So how many times is this if statement going to run? Well, it's going to run n times, right? Because we're iterating through n elements. And this statement itself, so this line contains two primitive operations, right? Because we've got an array indexing, and we've also got an equality check, right? So that's 2n in total because we've got n iterations. And then we've got a return statement at the end, right? So 1, and then if we sum all of these up, we get 4n plus 3. Right, so that's the number of primitive operations that would occur in the worst case. Right, so I see we're 5 to 3, so we'll take a break here, and we'll continue in 10 minutes. Right, and also, there are lollies again today. So you can come out to the front and grab some if you want. All right, so before the break, we counted the number of primitive operations that are performed by, sorry about that. Okay, so we counted the number of primitive operations performed in the worst case by linear search, right? And we came to the sum 4n plus 3. Right, so now let's see what we're going to do next. So now that we've counted the number of primitive operations, what do we do? So, so this is just repeating what I said. So linear search requires 4n plus 3 primitive operations in the worst case. And earlier we made the assumption that each primitive operation takes the same constant amount of time, right? C. So we'll use C, and that means the worst case running time of linear search is C times 4n plus 3, right? So that is the actual time that it takes for linear search to run in the worst case, right? And what this tells us is that since C is a constant, right, the worst case running time of linear search is linear, right, in n, the input size, which is basically confirming what we found earlier when we did empirical analysis. Okay, so now what we want to move towards is sort of simplifying this expression, right? So for linear search, we came up with 4n plus 3 primitive operations, right? With a more complicated algorithm, we could have, more terms, more, larger coefficients, something like, 5n squared plus 10n plus 3, right? Something like that. So we want to simplify that to get something that characterizes how efficient the algorithm is in a simple way, right? So first of all, let's have a look at the lower order terms, right? In this expression, 4n plus 3, right, 4n is clearly like the highest term, right? It's the largest term with the highest degree, and the lower order term is 3, right? In a bigger expression like n squared plus n plus 1, for example, n plus 1 would be the lower terms. Right, so remember that we're interested in how the running time of the algorithm changes as the input size increases, right, is scaled. So for example, if we double the input size, how does the running time change? If we increase the input size tenfold, how does the running time change? So as the input size increases, the lower order terms are going to become less and less significant, right? And for example, let's look at 4n plus 3 from linear search, right? If n is just 1, for example, like we're searching through one element, then the lower order term here does have quite a big impact, right, on the running time, right? But if n is 10, then the first part of the sum would be 40, and then we'll be adding 3, so 3 would be a much smaller part of the running time, right? And if n is 100, then the 3 would be even less significant, right? So as n increases, the lower order terms become less significant, right? And they become a smaller proportion of the running time. So what this means is that we can basically ignore the lower order terms because we're interested in what happens when we feed in lots of data into the algorithm, right? So like 10,000, 100,000, a million. Okay, so we can ignore lower order terms, but also what we'll notice is that the growth rate is also not affected by constant factors, right? So even here, we've got 4n plus 3. It turns out that the factor of 4 here doesn't really affect the growth rate. And what do I mean by that? So, suppose that we have another algorithm here, and its running time, Tn, is n squared. Right? So that's a nice and simple running time, and that's because we've sort of ignored the lower terms, right? Because we just said that lower order terms, they are insignificant when you get to larger input sizes. So if our running time is n squared, then what happens when we double the input size? Right, so this is a quadratic algorithm, n squared algorithm. So when we double the input size, so we're going to we're trying to find the running time when we give the algorithm 2n items, right? So what we're doing here is we're plugging 2n into this expression here, n squared, right? So we get 2n whole squared, and what does that equal to? That equals to 4n squared, right? And since n squared is equal to tn, our result is we get 4tn, right? So the amount of time taken by the algorithm quadruples when we double the input size, okay? And I can show you another example. So let's go over here. So running time.txt. Right, so here's another example. Let's suppose that our algorithm takes n squared time, right? And what happens when we feed in 5 times the amount of data? Right, so anyone want to hazard a guess? How long is the program going to take compared to, yes? Yeah, perfect. So 25 times longer, yeah. And the reason is that 5 squared is 25, right? But also, if you want to work it out thoroughly, then you would do it like this. So we're trying to find how long the program takes if you give it 5 times the data. So that would be 5n squared, right? And that equals to 25n squared. And that equals to 25tn. Because tn is n squared. So it takes 25 times as long. So let's look at another one. So instead of a quadratic algorithm, let's suppose we've got a cubic algorithm. So this time we're going to say tn equals to n cubed. Okay, so if we triple the input size, how much longer is it going to take compared to, originally? Yeah, 27, right? That's because 3 cubed is 27. So let's work it out. So t of 3n is going to be 3n cubed, right? And that equals to 27n cubed, which equals to 27tn. So, yeah, so we can see that for a quadratic algorithm, when you increase the input size by a factor of k, right, the time taken by the program increases by k squared, right? And if you have a cubic algorithm, then it would increase by k cubed, and so on. Okay, so when we double the input size, the running time quadruples, right? So at the moment, I'm trying to show that growth rate is not affected by constant factors. So let's suppose that instead of the running time being n squared, right, let's suppose that the running time is 10n squared, right? So now what happens? Well, we're going to try and plug in the same thing. So we'll plug 2n into our formula here. So t of 2n equals to 10 2n whole squared, right? So we're plugging 2n into this expression, and that equals to 10 times 4n squared, right? And now I'm going to do a little trick. I'm just going to swap the 4 and 10 around, It doesn't matter because we're just multiplying everything. And the result is 4tn, right? Because tn is 10n squared. So you see that no matter what the constant factor is in front of the n squared, like whether we have one or not, right? When we double the input size, the running time quadruples, right? So this shows us that growth rate isn't really affected by constant factors. So that's why we can get rid of those as well. Right, so to summarize, lower order terms become insignificant as n increases, so we can kind of discard those. And growth rate is unaffected by constant factors. Okay, so what this means is that we can ignore the lower order terms and constant factors when we characterize the growth rate of the algorithm. Right, so some more examples here. If Tn is 100n plus 500, so these are pretty big numbers, we can still ditch them. Right? We can ignore the 500 because it's a lower order term, and we can ignore the 100, and that gives n. Right? And n is a nice and simple expression, which tells us immediately that the algorithm is linear. Right? So another example, if Tn is 5n squared plus 2n plus 3, then we ignore the lower order terms, so we ignore 2n plus 3, and we ignore constant factors as well, so that would be the 5, and that gives us n squared. Right, so even though the first algorithm here had some really large constant factors, right, 100, and 500, this getting rid of the lower order terms and constant factors tells us that this second algorithm here is still less efficient, right? And we can show that in this graph here, right? So I've graphed 100n plus 500, which was the first algorithm from the previous slide, and I've also graphed 5n squared plus 2n plus 3, right? And you can see that even though 100n plus 500 is larger at first, it gets overtaken eventually by 5n squared plus 2n plus 3. Right? In this case, we didn't need that many inputs before the n squared algorithm overtook the linear algorithm, but you see, so even if the constant factor here was 1,000,000 instead of 100, right? Eventually it will get overtaken by the n squared algorithm. Right, so yes, question?
So if you ever run two algorithms at the same time, but then you find the intersect point and then take it, is it under the swinging terms from this algorithm, is it moving the swinging terms from this algorithm?
Yeah, that's a good question, yeah. So you could do something like that, for sure. Yeah, so the question was, if you're running two algorithms at the same time, and they were like this, would you choose to run one algorithm over the other depending on what the input size is? And yeah, you could. Yeah. Okay, so the point here was that for sufficiently large inputs, right, the algorithm that has the running time with the highest order term, which in this case is the 5n squared, will always take longer, right, for sufficiently large inputs. So for small inputs, it might not, but for sufficiently large inputs, from some point onwards, there's a threshold where if you increase the input any longer or any more, the algorithm with the high order term will take longer. Okay, so what is the advantage of discarding the lower order terms and constant factors? It allows us to easily compare the efficiency of algorithms, right? Because you've got very simple terms like n squared, n cubed, log n log n, and so on. So, if you are writing an algorithm to solve a problem, and your friend's also writing an algorithm to solve the same problem, right? If you both analyze your algorithms and you both end up with n, then you know that your algorithms are pretty, like they're in the same ballpark in terms of efficiency, right? But if maybe you come up with n and your friend analyzes theirs and they come up with n squared, then you know that your algorithm is more efficient, right? Okay, so yeah, so what was my example here? So if we discard lower order terms and constant factors, an algorithm A has a running time of n, and algorithm B has a running time of n squared, then we can say that for inputs that are sufficiently large, algorithm A is going to perform better. Okay, and I keep saying sufficiently large here because it's not necessarily, algorithm A is not necessarily going to be better for small inputs, but as the input size gets larger, algorithm A is going to be more and more likely to perform better because algorithm B grows a lot faster than algorithm A. All right, so yeah, another thing that we can do is, so we said that growth rate isn't affected by constant factors, right? That's what we said earlier. So what that actually means is that instead of counting primitive operations, which I just did before the break, instead of doing that, we can just count the number of line executions, right? And the reason is each line of properly structured code or pseudocode only contains a constant number of primitive operations, right? So imagine like let's look at the linear search algorithm. So it seems like the maximum number of primitive operations on any line in this pseudocode is 3, right? Because of this for loop. So it has the assignment, condition checking, and increment. So 3 primitive operations on the same line. So if we just counted the number of line executions, right, we would see that there are 2n plus 1 line executions, approximately, right? So that's because this for loop has n iterations, so we'll just say it runs n times, right? This if statement also runs n times because the loop has n iterations, and then we return a value at the end, right? So 2n plus 1. Now, if there are 3 primitive operations at most on each line, then that means there are at most 6n plus 3 primitive operations overall, right, in the worst case. I'm just multiplying the number of line executions by the maximum possible number of primitive operations on a line, right? And 2n plus 1, 6n plus 3, so those differ by a constant factor, so the growth rate wouldn't be affected, right? So yeah, instead of counting primitive operations, which can be kind of finicky, because remember back when we counted them, I had to imagine what the for loop looked like, right, if we implemented in C, just to count the primitive operations. So instead of doing that, we can just count the number of line executions, and that's a lot easier to do. Okay, so now we're going to talk about big O. So big O, so it's a notation we use to describe the asymptotic relationship between functions. Right, so what do I mean by asymptotic? That means we're concerned with what happens as the input size approaches a very large value or infinity, right? So that's what we say when, that's what we mean when we say asymptotic. And yeah, we use it to examine the relationship between functions, right? So what is the formal definition of big O? Right, so if we're given 2 functions, fn and gn, right, we say that fn is big O of gn if there are positive constants c and n0, such that fn is less than or equal to c times gn for all n greater than n0. So that probably didn't make a lot of sense to any of you because it's a lot of maths. So what I've written underneath is my interpretation, my informal interpretation of what that means. And hopefully that should make more sense because it's written in English. So given functions fn and gn, we say that fn is big O of gn if for sufficiently large n, so there's the sufficiently large again, fn is bounded above by some multiple of gn. Okay, and I'm going to show you some diagrams to explain that. Right, so here is an example. So we have fn here, so f of n is this function in the dark blue, and g of n, so this is not g of n, this is c times g of n in the light blue, right? And what we see here is that at the beginning, when the input sizes are small, right, the f of n occasionally overtakes c times g of n, right? So it starts up above, then it dips below, and then it goes above again, and then it dips below. Right, but that's fine because what we care about is what happens when the input size approaches a large value or infinity. Right, so we don't really care what happens with smaller inputs as long as, as long as f of n remains bounded under when the input size is large enough. Right, and important thing to note here is that we're multiplying g of n by a constant c, right? So in the definition, we said fn is bounded above by some multiple of g of n, right? So some constant multiple of g of n. So if we weren't allowed to multiply by a constant, then it's possible that g of n would end up lower than f of n, right? But since we're allowed to multiply by any constant that we want, so we have chosen the constant which would allow f of n to be bounded above by c times g of n. Right, so here we say that f of n is equal to big O of g of n. All right. So we'll go through a couple more examples. So here is an example where you might look at the right graph and you have no idea what's going on. So also the graph looks kind of weird, so I'll try and explain it. So suppose we have two functions, f of n equals 2n plus 10, and g of n equals n. All right, and what we want to show is that f of n is big O of g of n. Okay, so f of n is, so we have two solid lines here. F of n is the one above, right? It's the top one. And the reason it's curved, so 2n plus 10 is a linear function, but the reason it's curved here is because this isn't an ordinary graph, this is a log-log graph. So yeah, things might look a bit weird. But this is 2n plus 10, right? And g of n is the solid line at the bottom, right? So it's this straight line. Yeah, and what we want to show is that f of n is big O of g of n. That is, 2n plus 10 is big O of n, right? That's what we want to show. So remember the definition of big O, right? So the definition was f of n is big O of g of n if for sufficiently large n, f of n is bounded above by some multiple of g of n, right? So basically we have to find out what that multiple is, right? And what sufficiently large means. Right, so we need to find some c such that for sufficiently large n, 2n plus 10, which is our f of n, is less than or equal to c times n. Right? So c is our constant. And I'm not going to do all the working out, but it turns out that there is a constant. So for c equals 3, it turns out that f of n is less than or equal to 3 times g of n. Right? And that occurs when n is greater than or equal to 10, right? And you can see that in this graph, right? So 3n is this dotted line here, right? So like notice that if we didn't multiply n by 3, right? There's no way it would overtake 2n plus 10, right? 2n plus 10 is directly above n, and they're both growing at the same rate, right? So if we didn't multiply n by 3, there's no way that it would overtake 2n plus 10. But if we, if we plot 3n, then after n is greater than 10, it'll overtake 2n plus 10. So you don't really need to worry about this. Yeah, do you have questions? Sorry?
What's the significance of this dwarf? How would we use boundary functions?
So you wouldn't, because you wouldn't be asked to derive this stuff. I'm just demonstrating big O. Yeah. So I'm just explaining what big O is, and sometimes it just requires some examples. Someone have another question? Oh yeah, so you wouldn't have to solve these problems. Would you use it for anything? So you would use like I guess this shows us that f like 2n plus 10 is O of n, big O of n, right? So there are some like slides later that will that should clarify things. But just imagine that 2n plus 10 is like the number of primitive operations, right, that are performed by your program. Right, so that means that your program is big O of n, or your algorithm is big O of n. So your algorithm is linear. Yeah. Yeah, so we wouldn't ask you to do this analysis for those kinds of functions. Yeah. Yeah. Yeah, so here we're not really like comparing two programs. We're just taking, so for example, suppose this is like the running time of our program, right? And we're just showing that this this running time function would be considered to be big O of n. Yeah. That's what we're showing here. Yeah, so 2n plus 10 is big O of n. So I have another example here, which is where we don't get a result. So suppose we have a function n squared, right, and we have another function n, and we want to try and show that n squared is big O of n, right? Now, your intuition might be telling you that it's not and it isn't, right? That's because if you try and work things out, right, so you need to find some c such that for sufficiently large n, n squared is less than or equal to c times n, right? Now, this isn't possible because if you cancel out an n from both sides, right, that means c has to be greater than or equal to n, right? But that's not possible because c has to be a constant and n is a variable, right? So it's impossible. And the graph here also shows this. So we can see that the graph for all the linear functions, like n, 10n, and 100n, they all have the same slope here, right? But the graph for n squared has a much greater slope, which means no matter how large of a constant factor you choose, n squared will eventually overtake the linear function. Okay, so that's a bit of maths. Don't need to worry too much about it. But now let's talk about time complexity. Right, so time complexity is one of the big themes of the course. Right, it's the amount of time taken by an algorithm to run, right, as a function of the input. And in this course, we'll usually express time complexity using big O notation. Right, so for example, linear search is O of n in the worst case. Okay. And how do we determine the worst case time complexity of an algorithm? So we go through the process that we went through earlier, right? So you determine the number of primitive operations or line executions performed in the worst case in terms of the input size. So the input size will be n, and you have to get some expression in terms of n. Right. Then you can discard lower order terms and constant factors. Right, so you can discard, for example, if we go back to here, you can discard 2n plus 3. Here you can discard 500, and you can also discard the constant factors like 105. Okay. And then, so the term that you get left with, that is your worst case time complexity, right? So big O of that term, that is your worst case time complexity. So just let's go through an example. Right, so suppose you analyze a program and the number of primitive operations you've come up with is something like this, so 6n squared. Actually, let's spice it up a little bit. So 6n log n plus 5n plus 2. Right, so the lower terms in this expression are 5n and 2. Right, so we get rid of those, and we get left with 6n log n, and we get rid of the constant factor. So we end up with log n, right? And so the time complexity is big O of n log n. All right. Okay, so here are some very common functions that you'll encounter when you're analyzing algorithms during the term. Yes, question?
Yeah, so like if the whole, so back there when you had 6n log n plus a bunch of other things,
Yep.
would you use big O to say that time complexity would therefore be 7n log n for large amounts of all four of these for long items?
So for big O, we get rid of all the constant factors. Regardless of anything. So we can express it as simple as possible.
So would it then be 7n log n? Like is like the amount?
So, do you mean if we replace the 6 with a 7? Or?
Yeah, would that be what O of n log n is? Would it be 7?
It wouldn't be, so, well, okay, like big O of n log n, that's just a way of characterizing the running time of the input. So, like the real runtime could be something like 7n log n. That is possible, but we omit the constant factors because they don't affect the growth rate, and that's
Okay, so we just leave it as O of n log n?
yeah.
Okay, thank you so much.
All right. Yeah.
And when you say in the slides you can use the primitive operation or line execution,
Yeah.
are you saying that because at the end, regardless of which one you do, you're going to get the same answer? Because of the
Yes. Yeah.
Okay, so would you say you just use line executions because it's quicker?
Yeah, it would be faster. Yeah. Yeah. So the question was, so we were going through counting primitive operations and line executions. So, you know, so do we get the same result either way? And the answer is yes, we would. Okay. So yeah, so here are some common functions. So constant is 1, right? So it's O of 1. Logarithmic would be log n. Linear is n. N log n, so we'll see that next week when we look at sorting algorithms. Quadratic, which is n squared, we'll also see when we look at sorting algorithms. Cubic, n cubed, like exponential is 2 to the n. Or it could be 3 to the n or 4 to the n or so on. Factorial is n factorial. So these are listed in order of how fast they are. So n log n, for example, is faster than n squared. Right, and here's a visual representation of that. Okay, so you see it's labeled n squared, 2 to the n, n factorial as horrible, but there are some problems where the best solution you can come up with is n squared or is 2 to the n. So it's not necessarily horrible. It depends on the problem that you're solving. Right? Here's n log n, and here is on, and log n and O1 are so close together that they're almost the same. They're pretty indistinguishable. Okay, so we went through big O of n, but this is a slide just to let you know that there are other notations as well, which we won't really talk about in this course, but just to make you aware. So there's big omega. So first of all, what was big O? So big O is f of n is less than or equal to g of n, right? Big omega is saying that f of n is asymptotically greater than or equal to g of n, and this is big theta, which says that f of n is asymptotically equal to g of n. So don't need to worry about big omega and big theta. Big O is the only one you need to worry about in the course. All right, and this is just the definition of big O again. All right, so back to linear search. So linear search requires 4n plus 3 primitive operations in the worst case. So it's linear in the worst case. But can we do faster? So is there a faster way of searching through an array? And the answer is kind of yes and kind of no. So it is possible if the array is sorted, right? And this method, which we'll talk about, binary search, is fairly intuitive if you've played that game, that number guessing game. Like you have to guess a number between 1 and 100, and you guess a number, and then your friend tells you whether your guess was higher or lower, right? So if you're smart, you'd probably guess 50, right? And then because that eliminates the most options, And then, if they say higher, then you know the numbers between 51 and 100, so you guess like 75. And that's the principle of binary search. Right? So we start in the middle. So we check the middle element of the array. Remember that the array is sorted. So we check the middle element. And if the element we're searching for is less than that element, then we search on the left-hand side of the array, right? Because that side will contain the element that we're searching for. Otherwise, if the element we're searching for is greater than the middle element, then we search on the right-hand side. Right? And obviously, if the element in the middle is the element that we're searching for, then we're done. Right? So here is the code for binary search. Right? So we've got int low. Right? So we've got two variables here, low and high, to keep track of the bounds of the part of the array that we're checking. Right, so at the start, low is just going to be the lowest index of our array, and high is going to be size minus 1, which is the highest index of our array. Right? Then we check. So then we've got a while loop that keeps going while low is less than or equal to high. Right? So that means do we still have any elements to search through? Right? So if low eventually crosses around with high, that means we've run out of elements to search and we haven't found the elements. Right? And inside the while loop, we calculate the midpoints of low and high. Right? And then we compare the element that we're searching for with the element in the middle, right, of that section of the array. Right? So if it's less than the element in the middle, then so if the element we're searching for is less than the middle element, right, then that means we have to search on the left side, right? That means we adjust high so that it's equal to mid minus 1, right? Otherwise, if it's greater, we adjust low. So I've got a diagram to explain that, so don't worry. So I'll just show it now. Right, so here is our array, and suppose we search for 6. Right? So we compare the element that we're searching for, 6, with 5, and since 6 is greater than 5, right, we search on the right-hand side. Right, so we adjust low so that it's mid plus 1, which is index 3. Now the middle element is 8, right? So we compare 6 with 8, and 6 is less than 8. So we search on the left-hand side, right? So we adjust high so that it's mid minus 1. And now low, mid, and high are all the same. So we check this element, and it's equal to 6, right? So we found the element. Here's an example of an unsuccessful search. Right? So we search for 7. So we compare 7 with the middle element, which is 5. Right? 7 is greater, so we search on the right-hand side. Then the middle element is now 8. So since 7 is less than 8, we search on the left-hand side. So we set high to be mid minus 1, which is 3. And now low, mid, and high are the same again. So we compare 7 with 6, and 7 is greater than 6. So we adjust low so that it's mid plus 1, right? But now low and high have crossed over, so we've run out of elements, okay? And the while loop condition that I showed you before becomes false, right? Because low is no longer less than or equal to high. Okay, so to analyze this really quickly, so to analyze this, we notice that everything in the while loop, right, is constant time, right? All the operations inside the loop occur in a constant amount of time, right? So all that we need to know to analyze the function is basically how many iterations are there going to be, right? Well, in the best case, there's going to be one iteration because you found the element right away, right? So in this example, it'll be if you're searching for 5 and you just find it because it's the middle element. And in the worst case, so the worst case would be log n, right? Log base 2 n iterations, right? And the reason is every time you make a comparison, right, you are basically halving the part of the array that you're searching in, right? You're halving your search space. So the question is, how many times can you halve your search space before you run out of space, right? Until you have nothing left to search. And that would be log base 2 n. So we have log base 2 n iterations, and that would occur if the item doesn't exist. Right, and yeah, and this was the explanation of why it was log base 2 n. Right, so that means binary search is log base 2 n, or we can drop the base and just say log n. Yeah. It'd be base 2 because every time we make a comparison, we're halving the size of the array that we're searching. So we're dividing by 2 repeatedly. So number of times you can divide by 2 until you get down to 1 or 0 is log base 2n. Okay, and this is just some exercise that you can do on your own. So this was, yeah. So basically we're done with the lecture. So yeah, question?
When analyzing the worst case, why do you use big O instead of like because big O means like up and down, whereas omega means like exact. More exact.
Yeah, so that's a.
Why is big O more popular?
Well, I'll answer your question afterwards. But I want to say that so there is a consult right now from 4 to 5 in the K17 building. So if you want to come along, you can. Yeah.